I've been interested in long-term integrity from 1996, and it was in connection to the development of the Estonian Digital Signature Act, which started these years. And the agenda of my talk is the following. I will draw a generic picture of what we mean about long-term integrity. Then I will go through my favorite topics of the integrity of digital signatures and some cryptographic measures like digital timestamping. And then I go through formal security notions, which I've been defined during my research, and also I discussed their suitability in the quantum setting. Maybe some interesting future research questions arise. Okay, and then if I will have some time, I will also discuss, just summarize what happened in Estonia during the last decades in this field. Okay, so first, we cannot transfer information directly. All we know, we have to encode it to data. And the data is then transformed to physical signals, and physical signals can be sent from A to B. Also, which should be emphasized and which has not been emphasized in textbook very much, is that we also have to transfer the formats of data, the formats of encoding. We have several layers of encodings during the process. Okay, so somehow this format should be transferred to both A and B, either from A to B or B to A, or from a third party to both parties. For example, if we talk about internet communications, the RFCs are defining all the formats we need, almost all the formats we need for understanding the communications and being able to communicate. Okay, so let's start with the model of communication, what I think we all understand. We have threats during the communication. We have outside threats, which originate from outside the channel, and that's why we have fault tolerance mechanisms against that. Then we have threats that occur inside the channel. For example, noise. Then we need error correction, detection, codes, and we also have attacks. And for attacks, of course, we need cryptography. In usual communication, we need message authentication codes, digital signatures, maybe some more things, encryption. I just mentioned the mechanism that we need for integrity. So what we require for integrity is that data should stay the same for after transmission. Both A and B must have the formats. Both A and B must have the cryptographic keys if we use some. So if we look at the communication, then usually the distance is what matters. And the time is very short because mostly we go in light speed if we are communicating. So we usually need some assumptions to prove or to argue why all this thing is secure. For example, keys will not be invalidating during the transmission. So what if we get long-term integrity if we turn this communication axis towards to the time axis, from present to future? So I think we have exactly the same model. We have outside threats, we have inside threats. Maybe the cryptographic mechanisms are a bit different. Instead of message authentication codes, timestamps pop up as the most important mechanism. We may use qualified digital signatures, blockchains, etc. What we require is that the data should stay the same during the interval between two time moments, TA and TB. Also, we should require that the formats should not be lost during this interval, because otherwise we will not able to read the information. In this case, distance can be very small, even 0, but the time is that matters, and this can be very, very long. And maybe the assumptions we are making during the ordinary communications are not in place anymore. So we cannot expect that the keys will stay valid during this period of time. Okay, so what are the threats that are specific for long-term integrity? Of course, storage medium may fail, key exposure may occur or abuse. These are potential threats. We have revocation mechanism, as we know, this should be there if we look at the previous threat. We have weakened crypto because of, say, growing computational resources. Key sizes may get insufficient. The crypto may also be weakened because of some kind of revolutions in the computations like quantum computers, etc. And as in ordinary communication, we cannot send, it's much harder to send information from here to moon than from here to, say, to a kilometer away. So we may need few hops or many hops to send the information from past to the future. Okay, so we need some kind of regeneration steps during sending the information to the future for this to be readable. So some examples. If we have old data files, but we don't have the formats anymore, then of course the data will be useless. And that's exactly what happened in Viking Marslander, one of its tapes. They finally recovered it, but with a big effort. So this is quite practical threat. Example 2, digital signature on a contract. If you don't use any additional protection mechanisms, if something happens with a key, the signature will be useless. We may protect the digital signature with key validity confirmation, the OCSP response, and glue it together with timestamps. So this kind of signatures live until the timestamps are alive, reliable. Okay, and finally, if quantum computers are built that can factor real-life keys which shows algorithm, then we are in a big trouble, of course, if you use the signature mechanisms. So signatures may be broken quite suddenly, quite unpredictable. So timestamps, as I said, is one of the most important mechanisms if we consider long-term integrity problems. And maybe there are more, but I know two main types of mechanisms. One is the signature-based mechanism, which involves a trusted third party with a clock. If you send something to the party adds a correct time reading and signs the composition. Okay, so the other mechanism, it's known from 1990s already, the works by Haber and Stornetta. We just use hash function. So we have a third party which is not trusted in a sense, and after any time unit t, the party creates a hash tree from all the requests that it receives during this time unit and computes the root hash and then publishes the root hash to a trusted repository. We just have to trust that in this repository nothing changes. like a newspaper, for example. Okay, and what is the timestamp for an item, say xi, in this picture? X3 is just the slice of the tree, just the hash chain, which consists of the sibling hash values in the tree. So we can recompute the root from this item. And this somehow proves that this item existed before the root was created. If we use the hash function that is, at least we believe it is one way or has properties like that. Okay, so yeah, we use this kind of funny curvy arrow to indicate that there is a hash chain from a hash value xi to another hash value r, just to be simple. Okay, so what is the... I don't want to say that one mechanism is bad and the other one is good, but they're different. So, this difference, at least why is my sympathy on the side of the hash-based mechanisms, is that if you look at the signature, it may invalidate suddenly and unpredictably because, for example, leakage of the key. Sometimes we even don't know that the key is compromised. The hash-based mechanisms, they tend to break more slowly, more gradually, so we can predict the total breakage of a hash function. And we can react to the total breakage before it actually breaks. We can make a hop to the future before we are gone. Okay. So, and if we use timestamps to protect signatures, then it was very nice discovery. It was very simple, though, by Bayer, Haber, and Stornetta. I think it was in 1992 when they published a mechanism, a method how to protect timestamps with timestamps. And what you have to do before the old hash function that is suspected to be compromised soon, let this be the small h, all we have to do, we have to obtain a new timestamps for x itself and for the timestamp with the old hash function. So after, say, at t, this old hash function become totally insecure, still we have a proof that before t, we had a hash chain with an old hash function and x. So this means that still we can prove that this x existed before the time reading in the timestamp. That was created with the old hash function. Of course, using the new timestamps, which are secure. Okay, so my research has been focused on examining what we should require from hash functions, what we should require exactly to be secure for this kind of timestamping schemes. So it was thought before our research that it's a trivial consequence of the classical collision freeness property, but we showed that actually it's not the case. And what we actually need here, I don't know what we actually need there, but I proposed some conditions. And let's start from the requirement, or from the general requirement that we require from timestamps, that timestamps should reliably prove that certain data existed at time t. So the anti-goal, the attack would be that we somehow create fresh data, new data, and pretend as if it was much older. Yes, we backdate the data. And what kind of formalism we used is that we have an adversary that publishes a root hash, Maybe it was a representative of all the data items that were timestamped during T, but we don't know it. It might be arbitrary R. Then a random data item X is generated. This may represent as a description of scientific discovery or some technical novelty, whatever. And now we try to pretend as if it existed already before T. And then we have to create a hash chain that goes from X to R, C. So that's, I think this we should not be able to do. This is backdating. And what is fresh? We thought that freshness means in mathematics, it means unpredictability in some sense. So if something is completely predictable, how we can say it's fresh? How we can say it's new? It's kind of philosophical question. It's mathematical model, whether it describes the bad situation or not, even I don't know. Okay, so if we try to use mathematics to write this down, we had several ways how we wrote this down based on what we thought is reasonable. And the first condition, actually we wrote it down in 2004 in an Asia-Crypt paper, was that we have a two-stage adversary, A1, A2, and the success of the adversary, the attack scenario is the following. A1 publishes the root hash R and also gives out some advice. Then X is generated independent of the adversary, and then the second stage tries to backdate this X, which should be unpredictable. This distribution D should be at least have some entropy, reasonable amount of entropy. Okay, and well, then we thought that maybe the adversary also has some influence to X. Maybe it's involved in a process of invention. Maybe he also at least is able to create some bytes of X, some bits of X. And then we came up with a bit stronger, not just a bit stronger condition, which we called entropy-based security. It was, I think it was 1996 or something. And we removed this, we moved this generation of X into the second stage of the adversary. So the adversary itself generates X with a condition that X should be unpredictable, even if we know R and A that was previously generated. So we require that X should have at least some amount of min entropy. X should be unpredictable, even if we know R and A. Yeah, but we thought that it was more close to reality when the adversary may really have influence to X. Okay, so we proved several things. We proved that if we restrict the shapes of the hash chains, then we can actually prove that collision resistance implies this the first condition. This means that we cannot use arbitrary hash chains. The adversary has less freedom, but still we can rely on collision resistance, which is good. And we also showed that if we don't make this restriction, then it's impossible to prove the backdating security based on collision resistance. Okay. And also the second, which is interesting for this talk, is that the collision resistance also implies the stronger condition, the second condition, where we also restrict to certain shapes of the hash chain. basically the size of the tree that the adversary is able to create. Okay, but we can ask, what if we have quantum adversaries, which means that if A1 and A2 have a common quantum state, so what happens then? And just use the get notation here for A to mean that it's actually a quantum state, which A2 may also use. And it turns out that this condition is too strong. I mean, it can be easily broken with a quantum adversary. And what the quantum adversary does is that having, say, a 2-to-1 hash function H, it first creates the quantum circuit F that computes H in the usual way, and then we can create a superposition of all inputs and output pairs using the Adamar gate and the F circuit. And then we just measure the second register, that is actually R. There are, and now we get a superposition that is consistent with the measurement. So R should be on the right side of the register. And M is about 2 to the power of n, may less or more. And obviously, even if we know the quantum state and the published R, then X is unpredictable because the measurement is unpredictable. But of course, this adversary completely breaks the second condition. So, yeah, maybe some interesting conclusions. We can conclude that if there is just at least one hash function that is collision resistant in the presence of quantum adversaries, then collision resistant of H does not imply the shape restricted second condition. But remember that in classical setting, we could prove this, that this implies. So what it means is that we can ask what was done wrong in the quantum sense with A, the advice in this proof that we had. And the answer is that we use 2 copies of A. We can't use 2 copies of the quantum state. And so, and also any classical proof that implies the second condition from collision resistance should do something wrong with A in quantum sense. That's funny. Okay, so we can ask some theoretical questions. Is the quantum version of the chain resistance the first condition? Is it achievable? We don't know. At least I have no idea. It seems like it might be okay because X is chosen independent of the adversary. I don't know the way how quantum computer can be used to create a hash chain from this X to R, even if R was a large superposition. Even if A was a large superposition. But still we have to consider the possibility that adversaries have influence on this X that is backdated. So how to create a proper condition that is stronger than the chain resistance, but weaker than the second condition? What should it look like? I have no idea right now. Would be interesting. So, well, about my home country, it's a funny story. We started research on blockchains already in 1996. It wasn't called a blockchain, of course, at that time. This word did not exist. I think that's my personal opinion, nothing to do with Estonian official opinion, is that every country should, if it wants to care about long-term integrity, it should care about 5 things, define policies for 5 things at least. How to store data, where to store, which media, then format management, how to deal with fault tolerance, error detection and correction, and also the attack resistance. Estonia has archival law about the first point, but I'm not quite satisfied. It seems it does not systematically cover those topics. Estonia, of course, a small country, does not develop its own national formats. We try to support international standards. Of course, we have to use the existing built-in fault tolerance techniques. Maybe fault tolerance is not built-in, but certainly the mechanisms against noise. So what we have to consider is how to archive the devices that read some kind of information. That's also should be considered. Yeah, but of course, we have done something for attack resistance. As I mentioned, I started research already from 1996. And what happened is that I worked for Cybernetica, and Cybernetica has been a major strategical partner of the state through the decades. And we proposed actually a solution which was close to a blockchain, but maybe it was, I think it was premature a bit, and what was actually used was a kind of hybrid technology which used the PKIX type timestamps and a event log or hash type kind of thing. And yeah, of course, but now even this log was abandoned. We are in purely 3161 in the first, I mean, in the first type of timestamps where the signature is used. I mentioned why it's bad. And I think it was for unification with other country standards. I will not blame anybody, just funny, just funny to mention. Thank you.